Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to start talking about a very important concept with integrals called a line integral. And I absolutely hate the name because they really should be just called curve integrals. And I'll get to that in a little bit. But this problem is just kind of a vector field problem, kind of show you how we can use it to kind of do some predictions about where something might be at a certain time. So this vector field is like a velocity vector field, they're saying. And the x component is just given by x squared, and the y component of the vector is given by x plus y squared. And then it's saying if it is at position 2, 1, at time t equals 3, estimate its location at time t equals 3.01. So first, we should just find out what v of 2, 1 is. So v of 2, 1, right, would just be 4, and then 2 plus 1 squared is 3, all right? And then, so that's at, like, t equals 3, right? So at t equals 3.01, right, we should just be like 0.01 units time along that velocity kind of vector field some more, right? So that didn't make a lot of sense when it came out of my mouth, but basically what I'm saying is if you wanted to know where you were 0.01 kind of units of time later, you would just do 0.01 as a scalar on v of 2, 2, 1. Sorry, I was about to write 2, 3, 2, 1. And if you do that, then you're just going to get 0.04 and 0.03, right? And so that's how much further you should have traveled, right? Because you're basically, just scaled the velocity field by that amount. And so it's kind of a measurement of how much more you've moved. And so its new location would basically just be 2.04 and 1.03. And so that would be the new position, basically, just based on scaling that velocity by the unit of time. I can kind of think of it just honestly as like meters per second times second, right, would cancel and give you like the meters, like you've moved. That's basically what we're doing. So this right here is sort of how much you've moved. So we just tack it on to my original position. All right. So line integrals. So really they kind of should be called curve integrals, like I was saying. And they're basically just a higher dimensional 1D integral. And they could represent all sorts of different things in the real world. And there's actually a really, really nice animation, which I think is really helpful for understanding these. This thing is actually just from the wiki page on line integrals. But and I will show this in class because I think it's really helpful. But this picture is pretty good, and I'm going to kind of explain a lot of this other stuff here too. But you basically, what you're doing is you're taking a one-dimensional thing in the plane, like in the xy plane down here, okay? And the reason I like to think of it as a curve integral is you're taking like some sort of just curve. This could be like the thing you're integrating over, right? Like just something like that. But you're taking that bottom part, this part down here, that's like the curve you're integrating over. And all you're doing is you're basically just doing a normal old one-dimensional integral, and you're just sort of seeing whatever function you have, right? How much stuff is there between that function and the curve down here, right? So you're measuring basically the area between the curve in the plane and the surface, or like the function through space up here, right? So that is really all it is. It's kind of like if in Calc 1, right, what we're just doing is really those should be called like line integrals because you're just sort of saying like from A to B or something, you got some sort of curve up here, and you just want to know how much stuff is there between A and B. That really should be a line integral, in my opinion. And then this is sort of like letting this like pop out of a plane, right? Like we could think of it sort of over here. I could take this picture and put it over here. But now I'm saying let it pop out of the plane, and we'll give it some sort of three-dimensional piece, right? And when I do that, that's what we call line integral, but really it's kind of a curve integral. And this can be measuring all sorts of different things. These are just a few examples. So you could use this to measure the amount of rainfall along a certain like longitude or something, or like a weather front. So you can actually measure like, how much rain there is above like a front line or something like that. You could use it to measure like the height change in a road heading northwest or something. So you could, use it to just count up along a certain path, elevation gain or whatever. It's involved in like work, and we'll talk about that in another video actually specifically. Work is a physics term, and I'll talk about it when I get to it. But you can use them to calculate the magnetic field around a conductor, and there's so many different things. They are really, really prevalent in a lot of applications in science, but really all it is a normal integral, except you're letting it go over a curve that can kind of go through the xy plane, and then you're just doing a normal, how much stuff is there above it kind of thing. So this is the first kind of line integral that we're going to look at. There's actually going to be 3 ways that we compute these things, but one of them is actually kind of like the other one, so it's kind of like 2, but this one is very different than the other 2. So it says if f is defined as a smooth curve C, so this is the kind of thing I'm talking about, then the line integral of f along C is just written this way. Notice that there is a ds here, and you should think of arc length stuff, because that's really what we're doing here. And basically all this is going to do is, normal old kind of thing where I'm counting up how much stuff, I'm basically letting the intervals on the arc get smaller and smaller and smaller. So normal old kind of thing with integrals where I'm basically just like breaking up, this thing into smaller and smaller rectangles. Here what I'm doing is I'm saying n is like the number of sort of segments, like this is 1 segment, 2 segments, 3 segments, 4, 5, 6, right? And I'm breaking it up into more and more of those, and then I'm picking like a point in each segment, right? And I'm going to evaluate the function at that point, the function that's like, we can't really, we can't see the function in this picture, right? But like the function up here. And then we basically just do normal old length times width stuff to get the area, because we're just doing, this is like my height, you want to say, and this is like the length, and then we just multiply the 2. But as we basically break these curves up into more and more segments, right? If I just added a dot, I did a pretty bad job with some of these dots, but if I added a dot in between every other dot, right, and then I do the same thing, I get a better approximation of how much stuff there is above this curve and below the surface. So that is what we're doing. And we're just going to start off, and we're going to do a special kind of line integral today, which is like one involving arc length. So I want to go back to this first. So this is actually what we would call the parametric form of a line integral, and it comes out of ds dt, which is the kind of thing we saw with arc length. So this is, we saw this before, where this is just the square root of the derivative of like the x component with respect to time squared plus derivative of y component with respect to time squared, and you could scale that up to higher dimensions if you wanted. And so you could also multiply by like dt, And that would mean that ds is this thing, right? And so this is actually the formal kind of math behind what ds is, which is really just like the differential of that arc length, like these little segments, okay? Basically what this thing does is it finds the magnitude of the tangent vector and just kind of does an approximation of these like little segments with like little line tangent vector things. And those tangent vectors, if you make them small enough, they end up actually being perfect approximations of the arc. So this line integral thing, okay, integral of c, f of x, y, ds, could become this in parametric. So what we are doing is basically we're parameterizing x and y. So we have like x is x of t, y is y of t. And then this could all be nicely computed from that. And this is like the first way that we're going to find a line integral. It's a pretty straightforward thing. Honestly, the hardest part is doing the parameterization of the curve. So I actually want to go through this because it seems like kind of a silly problem, but I think it helps make some sense of what line integrals are doing. So imagine we had a curve, and I put it in quotes, connecting the point like A0, okay, to B0 over here. And so that's just like some curve down there. Then if we had something like that, we could parameterize that as just saying like x equals x. We could also do something where we say like let x be t if we want to use like t's instead of x's, but it really doesn't matter. But since the y is always 0, we could just say y equals 0, right? So then what we're really doing is, there might be some sort of function here. And what we're actually going to get is, what we should get, what I hope you see, is that we should just get our normal old integral that we did from Calc 1. And if I use this, but I plug in these parameterizations, we will get that, okay? So integral a to b, so I'm just like literally looking up here, and then I have f of like x equals t, or you could even say x is x. Let's just do x because it'll look a little more normal. And then we have 0, and then we have square root. Partial of x with respect to t is just going to be 1, right, squared. And then partial of y with respect to t is just going to be 0, t or dx, depending on what variable you want to use. But if you look at what we have, we basically are just doing f of x, square root of 1, well, really, I'm just not going to even write it, and then dx. And this really is basically just showing you that your like Calc 1 integral is really just a simple case of a line integral. And that is true. They're really just special cases. They're ones where this curve is basically smushed into a plane, and we don't have the kind of three-dimensional curve to it that you see here. So a little bit weird, and hopefully the concept's making some sense. I will show this video. I think this thing helps a lot. But what I want to get into now is kind of like computing some of these things. Oh yeah, and I do want to show this really quick too. So basically there's just a concise way to write line integrals. So if you think about what this thing is, right, just back from like vector unit, it is the magnitude, so square root of all the derivatives, and then the squared part comes from the magnitude, right? So you're going to have like like dx dt squared, and then you're going to have like dy dt squared, and you could have like another one, dz dt. Totally depends on how many components there are to this thing, but that could just kind of keep going that way. But that means that this part at the end right here, right, could actually, we don't have to write these line integrals with the weird square root thing. What a lot of times you'll see in textbooks is you'll see line integrals basically written this way. You'll see a to b or something, and then you'll have f of a parameterization, so f of like r of t. Okay, that's just kind of how they write it. But you have to realize that could be, you know, a three-dimensional thing or something like that. And then you'll have literally multiplied by the magnitude of r prime of t. That's like the part of this ds thing. And then you'll have a dt. Okay, that's really the way I'm used to writing line integrals. And, you know, these two things are literally multiplied together. All right, just like this, okay? So this is one I just want to kind of go through here. So we have this curve, C, and it's this like circular helix. It kind of just keeps going and going and going. And it's given by x is cosine, y is sine, which shouldn't be surprising. That's the circular part. And then z is t. That lets it go up into z. And we're going from t is ranging from 0 to 2 pi. So it's basically a full cycle. All right, so I think once you wrap your head around like all that conceptual stuff I was talking about with this, you'll see that the computation part's really not too bad. So, you know, this part is truly just like a magnitude of the like r prime vector. And so we would have like square root derivative of the x1 is, minus sine, but it's going to be squared, so we can just put sine squared t, and then derivative of y is cosine squared, cosine t, and then we're squaring it because it's magnitude, and then derivative of z is 1, we're squaring it, but we don't need to really square it. So this whole thing would just be square root of 2, right? And then we're going to go and kind of pop things in here. We're going from 0 to 2 pi, right? And then we've got y sine z. So we're doing like sine, let me try to color code this a little bit. So I'll do y in red here. So we're doing y, and then we've got sine of z, but z is t, okay? And so put a little t in there. And then we're going to multiply it by the magnitude of r prime, which is 2, and then dt. And then if you just kind of simplify this thing out, you could take, let's see, we'll just take that square root of 2 out. Then we got sine squared t dt. And for these kind of sine squared integrals, I would always just do the trig identity. This is the same as 1 minus cosine 2t over 2. And then you could like take a half out, root 2 over 2, 0 to 2 pi, 1 minus cosine 2t, dt. I dropped the dt over here. And then at this point, it's pretty nice. You know, you would have like easy integral here, and this one you can just like divide by the 2, and then there's like a minus sign in there. Evaluate the bounds. It's fairly nice. At this point, I think we've done a lot of integrals, so I'm going to kind of save the time of that part. You should get root 2 pi for that thing. But that is literally how you solve these things. You basically find a magnitude of the parameterization. You do f of r of t. This notation just means, you know, wherever y is, you put sine t here. Wherever z is, you put t. If there was an x, you would have put cosine t. And then you just solve out the integral from there. And that is literally, what that means is it's the amount of stuff under this function and above this curve in space from 0 to 2 pi. Okay, that's all we just did. Another nice thing about these things is that they're additive. So if we had something like this where we wanted to evaluate, like this whole thing is curve C. So we want to evaluate the integral over curve C of 2x ds, and C consists of the arc C1, which is x squared from 0, 1 to 1, 1. And then the vertical line segment from here up to here is C2. If you wanted to do like this line integral, you could actually just do it additively. So the the fact that integrals just add nicely like that means that you can do a line integral over curve 1, a line integral over curve 2, and then just add the two things basically together. And that's kind of how we would do it. So and that's kind of what's summed up down here. Like if you had more and more paths, like you might have even like 20 different paths or whatever. But if you wanted to find the integral, the line integral over that whole arc, right, then you can just like break it into easy chunks and just add up all those chunks basically. That's all I'm saying down here. So so we'll kind of do like one integral over here. So the first one is that y equals x squared one. So we're going to let basically just x be t, and then y is equal to t squared, right? That's like how we could parameterize y equals x squared. So then my integral, this one is going 0 to 1 in t, right? Because x is t, so we got to go 0 to 1. And then we've got 2 times x, but x is t. And then we've got to have the magnitude part in here. So partial of it's really just true derivative of x with respect to t is 1, squared is 1. And then the other one is just going to be 2t squared, which maybe I'll just write it. So 2t squared is going to really be 4t squared, right? And so that's my magnitude part, and then I have dt. And then it's a nice u sub problem. You can do u equal 1 plus 4t squared. Du is going to then be 8 t dt. And so I have a 2 in there. So really du over 4, right, is going to equal 2t dt, right? So then I could do 1/4 integral, where was it? T, oops, no, I got the t out with the du. So really I just have square root of u du, right? And so then you can solve that. You put the bounds back in. Again, we've done so much of this lately. I'm just going to tell you, you should get 5 square root of 5 minus 1 over 6 after you do all that stuff, okay? That's curve 1. Curve 2, let's do a different color here. Curve 2, we have the vertical line segment. So this part is curve 2, this was curve 1. So here I'm going to let x just be 1, right? And then I'm going to let y equal like y. Or you can just think y equals t. It doesn't really matter. So the integral over curve 2 of 2x ds would just equal, we're going from 1 to 2, right, in y, right? And then we've got 2 times, 2 times 1, which is x, right? I'll just put it in there. And then we got magnitude of 1 squared plus 1 squared, right? Oh, wait, no, sorry. The derivative of 1 is definitely not 1. So that should be a 0 squared. And then what we're basically doing here is like, so we're doing like a dy integral, right? Because we're just integrating the change in y. That's all that's changing, right? There is no change in x. So this is like, has simplified this line integral down to just like a 1D integral from here to here, basically. Like a true kind of 1D integral that you do in Calc 1, basically. And that whole thing looks kind of complicated, but it's literally just 2 if you do it out. And then now we can just go and add these two things. So we know that if we do the integral, the line integral of 2x ds, because of this whole thing being additive, it's really just curve 1 of 2x ds plus integral of curve 2, 2x ds, which is, if you add those together, let's just write 2 plus 5 root 5 minus 1 over, it's bad, minus 5, minus 1, I mean, over 6. So I'm sure it simplifies, but I don't care. But that's the idea. So anytime you get these vertical or like horizontal parts, you can really just think of it as, if it's vertical, it's going to just be a dy, right? Change in y. If it was like a horizontal line segment, then it's just like a dx integral, the way you do it in like Calc 1, truly, right? So those can sometimes kind of confuse people, but it's really simpler than you might think. That's all it is. So I just want to do one more example. This is basically a line integral in 3D, which is kind of good to see. So these ones were just like two-dimensional examples, right? But there is nothing wrong with extending this idea like we're doing right here. You can extend it to n dimensions. It's totally fine in any dimension at all. But so what we're going to do here is we've got C is the line segment from 0, 0 up to 1, 2, 3, which is, I don't know, we're going to say there. So 1, 1, 2, 1, 2, 3, kind of just like that vector. And the way I would just parameterize this, if I go back to kind of chapter 12 stuff, right, we have like the general kind of structure. Oops, I skipped a very important part. The general structure of like a line is a point it goes through, which we could just do like an easy one, 0, 0, 0, and then a direction vector for that line, which is like right here. You could just take the direction vector 1, 2, 3. So this is saying that x is equal to t, y is equal to 2t, and z is equal to 3t. Now you have the parameterization. You can do the magnitude. So, maybe we'll do r prime here is just going to be 1, 2, 3, right? And then the magnitude of r prime is the square root of all those things squared. Oops, I don't know why I cubed it. And that thing is square root of 14. So now we have the integral from, in terms of the time, right, at time 0, you're at 0, right? And if you want to be at 1, 2, 3, that time would be, so where it ends, right, is t equals 1, right? T equals 1 would get you 1, t equals 1 would get you 2 here, and so on. So we're going from 0 to 1, and then we're integrating x, which is t, e to the y, which is 2t, z, which is 3t, and then square root of 14 is my magnitude, and then dt. So this part, again, is all of the ds stuff, okay? So then we could simplify this and just get 2t to the 4th, e to the t to the... I'm sorry, I was looking at the wrong thing there. I don't know what I was looking at. So it's going to be t e 6t squared, right? And then square root of 14 dt. And I'm not going to spend too long solving this one either. I would do u equals to 6t squared, because then du is 12t dt, right? And so you have a t dt, right? So du over 12 is t dt, and you could pop that in and just do a u subproblem out. That's basically how I would go about it. I will tell you that basically once you plug everything in, you should get a weird, messy answer. Square root of 14 over 12, e to the 6 minus 1. That's what you should get. But that is basically just how we do it in higher dimensions. It's really no different. It's just more work. And one of the trickiest parts is definitely just how we even parameterize these things with t here. And that's definitely the tough part about doing line integrals this way. I will actually show you in the next video on line integrals some kind of shortcuts that we could use to help us do parameterizations easier.